particularly in the videos. I think mine is a little bit longer, I think, than Buhelen's videos. But anyway, you should be able to make use of all of those. All right. But before I start with the RCBD, I would like to repeat or to reiterate some of the basic, really fundamental concepts of Anova, which you guys have learned last week. Just so you guys can recall the important concepts, because Anova is really the cornerstone of basically all of the statistical analysis of experiments. Okay, so it is that important that you need to know what Anova is. Of course, I'm not asking you guys to remember all of the details in the mathematical steps involved in Anova analysis, but at least you should know what Anova is, what it does, and how to interpret the data. And with time, you guys should also have some experience in performing the Anova yourselves, either using Excel for simple cases or some other more sophisticated softwares like Minitab for more complicated experimental designs. Okay, so with that, let us start. Let me share the. Okay, here we go. Now, again, this file that I'm showing you now, I think it has been uploaded more than once. I think it might have been uploaded in the other module, in the past module in EduNext. But anyway, even so, that's fine. I'm just re-uploading it last night. Okay, so this one talks about experiment as a system. So we in chemical engineering like to think of things as systems where we have the system itself and we have input variables and also output variables. Now, experimentation is just one of several ways to perform study in chemical engineering. Okay, so the gist of experiment is the core concept of experimentation is that we manipulate these experimental factors and we observe how changes in experimental factors influences the response variable. Okay, now there are three input variables to a system, to an experimental system. The number one is the experiment factors themselves. So these would be the variables that we systematically change and measure their impact on the response. Okay, so these would be the variables of interest. But we also have what are called nuisance factors. Okay, so these are factors that we do not deliberately study, but ones that may influence the response. Okay, and nuisance factors can usually be anticipated. It can be understood. Okay, and so it is categorized as a systematic variable. Systematic means you can understand its values, you can understand the mechanism by which it affects the response. Okay, as opposed to the last one, which is the noise, and this is really a random factor. So this means that there's no way that we can pinpoint what these noises are. Okay, so the effect of that the noise have on this response is random. Okay, and in the last week with Buini, what you guys have learned is what we call a one-factor fully randomized experiment. Okay, and one of the most important characteristics of such experiment is that it only measures one factor. Okay, it only measures one experimental factors and it ignores any nuisance. Ignores meaning the experiment cannot measure these nuisances. Okay. Okay, so one systematic variable plus the random noise. Okay, and then, whoops, sorry about the typos. I think this is an old file actually, so there's still these typos abound, I think. Okay, so general approach in doing experiments in chemical engineering. The first one is probably the most intuitive. This is called an OFAT, or one factor at a time approach. So let's say that you guys have four factors, for example. Okay, you have four variables. Oh yes, by the way, in statistical language, factors and variables are the same. Okay, so let's say that you have a 4-factor experiment. Okay, and in an all-fact approach, what you do is you vary the value of just one factor while maintaining the rest of the factors constant. And you take turn doing this to each of the factors until you exhaust all of the factors. Yeah. So that is quite intuitive actually. However, it does have its weaknesses. All-fact approach is time consuming. It will you will end up with more number of runs, okay, compared to statistical experiment. Okay. Oh, what the hell is wrong with this? All right. And another main weakness of this OFAT approach is that OFAT cannot measure interaction. Okay, it cannot measure interaction effect between 2 or more factors. Okay, and in some cases that can be a serious disadvantage. Another approach is what we call best guess approach. This is done a lot actually in the industry where we have frequently the goal of an experiment is not to find something fundamental, but to make incremental changes or incremental improvements to your process or to your product. So you might want to improve some product formulation, for example. Okay, so now you can imagine if you work in a chemical processing plant for years, okay, then pretty much you know the behavior of your process plant, right? Let's say that you're in charge of a consumer goods product, okay, and if you given enough experience, you pretty much have a good feeling about the behavior of your process and how it impacts your product. Okay, so naturally, the natural extension of that thinking is that if you guys are asked to improve your process, then you most likely that improvement will involve small changes, right? Maybe a small shift in reaction temperature, for example, a small shift in feedstock formulation. So because you already have enough experience, then you can pretty much guess, okay, quote unquote guess about what a better setting should be. Okay, this is why we call it the best guess approach. Okay, it doesn't work in a lot of cases. Okay, it works only if you have prior experience with your system. Okay, and the last one, which we emphasize on this class, is the design of statistical experiment. Okay. Geez, sorry about this, guys. Better. Statistical design experiments. Okay, so these are experiments in which the design, meaning when we say experimental design in this context, okay, we don't refer to experimental procedures. Step 1, mix reactant A and reactant B. Step 2, turn on the stir. Step 3, have your thermometer ready. So that's experimental procedures. But when we say experimental design, what we mean is how we arrange the settings of experimental factors within each run. Okay, so run number 1, variable number 1, what is the setting of variable number 1? What is the setting of variable number 2, and so on. Run number 2, again, so what is the setting of variable number 1, variable number 2, and so on. Okay, so how we organize the values of experimental factors from run to run, that's called experimental design. Okay, so that's different from experimental procedure. Right. So, and the advantage of statistically designed experiment is because it is based on the science of statistics, then it can easily be, the data can be very easily and very quickly analyzed based on statistical principles. And you will have a very strong argument on whatever result, whatever conclusion that you're putting forth based on your experiment. Okay. Remember what we said a few weeks ago, that all engineering measurement will involve uncertainty, right? Measurement uncertainty is really the fundamental cause of why we learn statistics. Okay, We don't need statistics if everything is certain, but nothing is certain, okay? Any measurement variable will involve some degree of uncertainty, and that is, again, that is the really reason why we need to learn statistics, okay? And given that thought, when we perform experiments in the lab and we know that any experiment will involve measured variable and any measured variable will involve some degree of uncertainty, then we can be sure that our experimental result will contain uncertainty. And every time we're dealing with data that contains uncertainty, then statistics is the only universally accepted method. Okay, this is the reason why statistics is so important for any branch of engineering, chemical engineering, mechanical engineering, engineering physics, industrial engineering, you name it. Okay, all of us in engineering needs some degree of statistical knowledge because all of us are dealing with uncertainty. Okay. All right. Okay. So this is just some fundamental concepts in conducting experiments. Randomization, meaning that later on we will show you what standard run order is, ya, urutan tempuhan standar. And when we perform when we execute the experiment in the lab, we must not run it according to the standard order, but we have to randomize the run order. Okay, that is, and this randomization is important to minimize systematic errors. Replication. Okay, there's no way of telling how precise your experiment is unless you do a replication. Okay, jadi replikasi atau pengulangan percobaan ini sangat penting. Kita tidak akan bisa mengetahui berapa presisi percobaan kalau kita tidak melakukan replikasi. Dan replikasi ini tidak sama dengan pengulangan pengukuran. Jadi begini, you need to be able to tell the difference between replication of complete experiments and repetition of measurement or analysis. So let's say that you run an experiment in the lab and you generate, let's say, a bucket of product, okay? And then you divide that bucket of product into 2 samples, which you will then submit to the lab for analysis. Now, that is not experimental repetition. That's just analysis repetition. Okay. When we say a complete repetition on the experimental run, it means that you replicate everything from step 1 to the last step. Okay, not just making a big batch of sample and then divide the batch into 2 or more analysis. Okay. Okay, so again, I hope you keep this in mind. You need to randomize the order by which you run the experiment. You need to replicate the experiment to obtain precision. And then you also need to consider blocking. Okay, we'll talk a little bit more about blocking today. Right, and then we discussed some example on one factor fully randomized experiment. Okay, and illustration of the concept of Anova. Okay, now let's say that this is an easy case to imagine, I would say. So let's say that we have 2 groups of rice paddies. Okay, so on the right hand side here, these rice paddies are planted, are grown without using any fertilizer. Okay, and the one on the left hand side, this batch of rice paddies use fertilizer number A. And we assume that all other conditions are equal lighting, equal soil characteristics, equal watering, and so on. Okay. And of course, we can imagine that if the fertilizer A is indeed effective, then you will see taller plants after a certain amount of time, right? So again, if the fertilizer works, then you will see that the plants grown using fertilizer will be taller than the ones grown without fertilizer. Okay, and naturally, since you guys have studied hypothesis test, then of course, if you want to confirm whether the fertilizer is indeed effective, of course, you can perform a 2-sample t-test, right? Okay, And what you measure is the average height of these rice paddies, okay, with and without, with versus without fertilizer. And you can check that using t-test. No big deal, right? Now, how about if we add one more fertilizer, fertilizer number B, okay? Um, you might think that you can perform pairwise t-test, okay? So for example, we can perform t-test on sample fertilizer A versus without fertilizer, and then fertilizer B versus without fertilizer, and then fertilizer B versus fertilizer A. Okay, can you do that? Yeah, you can, but you will lose. You will have to compromise your probability of error. Now remember, it's not. We're not saying that our mathematical procedure is wrong, but remember, we are dealing with data that contains uncertainty. Okay, that cannot be avoided. And because we're dealing with data that contains uncertainty, then any statistical inference that we perform based on the data, whether it's calculation of confidence interval or performing hypothesis test. So those procedures will also contain some degree of probability of error, right? You remember type 1 and type 2 error, okay? And if we want to be correct in drawing conclusion about if there's any difference between these rice paddies, then we have to be correct in all of those t-tests that we talked about a few minutes ago. Okay, and the probability of arriving at the correct conclusion of all t-tests is not very good. Okay, the probability is so if we're using 95% confidence level, okay, 95% probability that we're not making a mistake, then the probability of not making a mistake for all pairs, for all t-tests simultaneously, is 0.95 to the power of the number of pairs. Okay, so in this case we have let's see, 1, 2. Okay, so A and without is 1 pair, B and without is 2 pairs, B and A, that's 3 pairs. So we have 3 pairs of t-test. Okay, so the probability of arriving at the correct conclusion for all 3 t-tests is 0.95 to the power of 3. Okay, the more treatment level that you have, the lower that probability becomes. So that's not such a good idea, okay? So we need something, a fundamentally different approach to analyzing this type of data, okay? So again, to repeat, if you only need to make comparison between 2 sets of data, that's fine. You can use t-test. But if the number of data sets, or we call it in statistics, the number of treatment level is more than 2, then it becomes not very attractive to perform a pairwise t-test. Okay. Let me repeat this in Indonesian for those of you who still couldn't follow it. Jadi gini, kalau misalkan kita hanya dihadapkan pada 2 set data, ya katakanlah misalkan yang pakai pupuk A dan tanpa pupuk, maka memastikan adanya perbedaan antara keduanya cukup dengan t-test. Kalau sampelnya kecil pakai t-test, kalau sampelnya gede kalian bisa pakai z-test, ya, uji hipotesis 2 sampel, no big deal. Ya. Tapi kalau jumlah sampelnya, ingat bedakan antara jumlah sampel dengan ukuran sampel ya. Yang kalian lihat di gambar yang kita tayangkan ini, jumlah sampelnya ada 3, ya. Fertilizer B, fertilizer A, and without fertilizer. So we have 3 samples. Kita punya 3 sampel. Nah, kalau sampel sudah lebih dari 2, pendekatan t-test atau z-test tadi untuk 2 sampel itu menjadi tidak akurat lagi. Bukan tidak akurat sih ya. Dia akan memiliki peluang kesalahan yang tinggi. Ya. Katakanlah kita mau menggunakan tingkat keyakinan 95%. Oke, 95% confidence level. Artinya kalau hanya bicara 1 pasang, ya, probabilitas kita tidak melakukan kesalahan tipe 1 adalah 95%. Nah, itu kan makna dari tingkat keyakinan 95%. Oke. Nah, sekarang kalau ada 3 set data, maka kita akan dihadapkan pada 3 pasang t-test, yaitu A dengan tanpa pupuk, B dengan tanpa pupuk, dan pupuk B vs pupuk A. Ya, jadi ada 3 pasang sekarang. Artinya, peluang kita tidak melakukan kesalahan tipe 1 untuk ketiga uji tadi secara serempak adalah 0,95 pangkat 3. Jadi jauh lebih kecil daripada 95%. Ini kan bukan tingkat keyakinannya bagus tuh ya. Ya. Semakin banyak sampelnya, jumlah sampelnya semakin banyak, peluang tadi semakin kecil. Peluang untuk tidak melakukan kesalahan tipe 1 untuk semua pasangan. Ya. Nah, karena itu kita menggunakan konsep ANOVA. Okay. So the basic concept in ANOVA, so what we do in ANOVA is instead of looking at the sample mean, what we look for are changes in the total variance of these rice paddy heights. Okay, so you can imagine if the fertilizer is indeed effective, then if we compare, if you can imagine a whole field, okay, several fields of rice paddies, some of these fields use fertilizer A, some of them use fertilizer B, and some of them does not use any fertilizer, then you can imagine that there will be a larger variation of heights, right? As opposed to not using any fertilizer at all, or using just one type of fertilizer, right? So if you sort of close your eyes to fertilizer B and A, and just looking at the rice paddy without fertilizer, even within themselves, of course, there will be variations in heights, right? This is the random error associated with the experiment. Okay. So it's God-given truth that there will be variations in plant heights, right? You cannot reprogram the heights of the animal. So even within one sample, you will see variations. You will see variance. Okay. Now, if some of these rice paddies receive different treatments, and if that treatment is indeed effective, then the total variance of the plant height will increase, right? This one. If fertilizer has effect on rice plant growth, then additional fertilizer will increase the total height variance. We no longer see the height of individual samples, but we see the total variance and how that changes with the treatment level. Okay. Right. So anybody has not get the basic concept, the truly basic concept of ANOVA yet? So again, what we look for is changes in overall variance and what contributes to that change. Okay. All right. So we invoke the Anova model. Okay, the FX model for Anova. We call this linear equation as the Anova model, where every data point, can be written as summation of these terms. Okay, so y sub ij, this represents individual measurement. Okay, individual measurement data, data individual, and then mu is the overall mean of all of your observation. Ya, rata-rata global. Jadi kalau kalian melakukan percobaan, kemudian semua hasil percobaan kalian rata-rata itu ketemunya mu itu. Okay, and then tau sub I is the effect of changing the treatment level. Okay, in our rice paddy case, the treatment levels are 0 fertilizer versus fertilizer A versus fertilizer B. So we have 3 treatment levels in our rice paddy example. Okay. And then we have epsilon sub ij, this is the random error component. Okay, so the value of each measurement data is a summation of the global mean, global average, plus treatment effect, and also random effect, random error. Okay, right? Now, with that in mind, These are the mathematical procedures of ANOVA. It can be quite lengthy, of course, but let me just show you the essentials. Okay, the total sum of squares. Let me fix that first. There you go. Okay, understand the meaning of these quantities, sum of squares. Yeah, jumlah kuadrat. So that's the Indonesian term for it. Okay, jumlah kuadrat or sum of squares. As the name implies, these quantities are summations of squares. Ya, penjumlahan dari sekian banyak suku kuadrat. When it comes to total sum of squares, okay, the formula is the square refers to the difference between individual data points and global average. Ya, jadi SST atau total sum of squares ini adalah jumlah kuadrat. Nah, apa yang dikuadratkan? Yang dikuadratkan adalah jarak atau selisih. What did I do? Wait, I move something. There you go. Jadi yang dikuadratkan adalah selisih antara data individual dengan rata-rata global dari data tersebut, dari seluruh data pengukuran. Okay, so you take the difference between individual data points and the global average, and then square them for and do that for all data points, and then sum it up, and you'll obtain the total sum of squares. Okay. And then what we do is we perform a series of derivations that we can you can look at about the details of these derivations in our textbook. Okay, this one here, design. Sorry, actually this is a different book, but this one is also easily obtainable. This is Montgomery's book, which deals exclusively on design and analysis of experiments. Okay, and it will be obtained that the total sum of squares is a summation of two components. Okay, two components. Sum of squares of treatments, SS treatments, and sum of squares of error. Okay, so we have two components, we have two distributions. The first one is a systematic contribution, and the second one, the last one, is always a random contribution. Okay, and these are the mathematical definitions of each of those SSs. Okay, so SS treatment is this one here. This is we call this a cell average. Okay, so this is the average within each treatment level. Yeah, going back to our rice paddy. Okay, going back to our rice paddy, you can see here, right? You can see in my computer screen. Yeah. So going back to our rice paddy experiment, this quantity here, y bar sub I dot. Okay, so this is the cell average or the treatment level average. This would be the average height within each sample. Okay, average height of rice paddy without fertilizer, with fertilizer A, and with fertilizer B. So in our case, in our rice paddy case, we have three of these numbers. Okay, so one for without fertilizer, one for fertilizer A, and one for fertilizer B. Okay, we call that cell average or treatment level average. Yeah, minus the global average. Okay, so we have three treatment levels. Okay, so this sigma, this summation will consist of three terms, one for each treatment level. Okay, and then the last one, sum of squares of error, is refers to the sum of squares of the difference between individual data points and its cell average or treatment level average. Okay, so this one you can look at it within each sample. Okay, again, please follow my cursor. Okay, So imagine you're looking at the right-hand side here. This is the rice paddy without fertilization. Let me zoom that out. Ah, okay, that's nice. There we go. Okay, right. So this is, oh, that's not nice. Okay, this is the height of one rice paddy plant. Okay, and this is the average rice paddy plant height in one sample to which this data belong to. Yeah. Okay, so for example, this would be the difference of height of one piece of rice paddy plant uh, against the average height within that sample. Okay, this one here. Okay, I think that's pretty clear. And then you sum up this difference for all of your measurement data, and you will get the error sum of squares. Okay. Okay, so this is what we call partitioning the variance. Okay, so we've partitioned the total sum of squares into treatment sum of squares plus error sum of squares. All right. And then what we do is we divide the SS with with the respective degree of freedom. Okay, so SS divided by degree of freedom equals to mean squares, MS. Okay, and mathematically, MS behaves just like variance. Okay, ya. Jadi kita lakukan sum of squares tadi, jumlah kuadrat tadi ya, itu dibagi dengan derajat kebebasan masing-masing. SS dibagi derajat kebebasan itu menjadi mean square, MS. Dan MS itu kelakuannya secara matematik menyerupai besaran varians. Varians ya, sigma kuadrat ya, kuadrat dari simpangan baku. Oke. Nah, apa yang kemudian kita lakukan? So what we do next is we formulate this so-called Anova Table. Okay, this is the traditional way of presenting results of Anova analysis. Anova, by the way, sorry, I forgot. Anova stands for analysis of variance, by the way. Okay, so the first column tells us the designation of source of variation. So we have between treatment variation or variation due to treatment level. And then random variation or errors within treatment variation and total variation. Okay, and the second column is usually the sum of squares. Yeah, third column is the degree of freedom. Fourth column is the mean square, and the last one is an F0 quantity. Now, the reason why we calculate the quantity F0 again. What we want to prove in ANOVA analysis is which one is more predominant, right? Which one is more significant? Does the total variance of the experiment mainly caused by treatment or by random error? Okay, so which one contributes more to the total variance of the experiment? That's the basic of ANOVA. In other words, we want to test which one is larger, right? Is it MS treatments or MS error is the larger one? So we want to compare two variants. Now remember, if we want to compare two variants, then what we do is we perform an F test. You've learned about it in the hypothesis test, right? Okay, so the F0 is formulated like this. So the F0 is MS treatment divided by MS error. Okay, and what we do next is simply to find, we can compare the F0 with the critical F value, just like what we do in any hypothesis test. Or we can use the p-value approach in drawing conclusion from the Anova table. And then actually, because as you can see from the formula, Anova procedure is quite lengthy, so we almost always use a computer to perform Anova analysis. And the statistical software that we typically use for Anova analysis can also calculate p-value. So it's very rare for us to use the traditional approach in hypothesis test, meaning we compare the f0 with critical f value. Okay, usually what we do is just we compare the p value with the alpha. Okay, or the significance level that we choose. All right. Okay, any questions so far? See, you can see the p-value here. Okay, so what we do with the p-value is we compare that to alpha. Okay, if the p-value is less than alpha, then this experimental factor is indeed significant. Okay, or it significantly influences the response. Ya, jadi setelah ketemu p-value ini kita bandingkan dengan alpha dengan tingkat keberhasilan. Katakanlah misalkan kita pilih alfanya 5%. Ya. Kalau p-value-nya lebih kecil daripada alfa, maka artinya variabel apapun yang kita pelajari di sini ini berpengaruh secara signifikan terhadap hasil percobaan. Atau kalau mau dibalik, hasil percobaan dipengaruhi secara berarti oleh variabel percobaan. Oke. Dibandingkan error, ya dibandingkan random error. Oke. Alright. Okay, it's now 7:46, so let's take 5 or 10 minutes break. Okay, let's make it 10 minutes, and we will continue with this one, the next one, the RCBD experiment. Okay, so if you guys need a glass of water or tea or coffee or whatever, so we'll meet in 10 minutes. Okay, so we will meet at 5 minutes to 8 a.m. and I will continue explaining about the RCBD experiment. Okay. All right, let us continue. So this is the main topic for today, and the reason why I'm saving this for the last hours, actually because this is a short topic, this is a short discussion. So I would rather give you guys a review of the Anova concept rather than um, delving directly to RCBD. Okay. Okay, so RCBD stands for Randomized Complete Block Design, and the motivation behind this experimental design is actually this one here. Okay, so nuisance factors are abound in our experiment in our daily lives. Okay, for example, um, you and your partner, for example. So when several years from now, when you guys do your senior research project, okay, penelitian 1, penelitian 2, you will have to work with partners. So typically, a student works in groups of 2%. Okay. Now, because you're not your partner, so there will be some variations between how you and your partner do your work, right? And that may also impact to the measurement results. Okay, so there will be variations between partner A and partner B. Okay, when you do your experiment, and that in itself is a nuisance variable. Okay, of course, it's not very useful to put in your thesis to put in your senior thesis report that in conclusion, me and my partner perform differently, right? I think that's a we can consider that to be a trivial observation. Okay, trivial is not wrong, but it's not useful. Okay, yeah. So bottom line is these nuisances are factors that we know it impacts our response in a systematic manner, but we're just not interested in them as experimental factors. It could be changing seasons, for example. You're doing experiment on drying, for example, and you can always imagine that performing a drying process in the dry season versus rainy season will give you a significantly different result, right? Unless you do something with your drying air, that is. Okay. Another example would be raw materials. Okay, let's say that in your experiment, in your research, you have to use more than one batch of raw materials. Okay, same raw materials but different batches. Okay, and you have to take into account the variations between batches without really assigning batch number as an experimental variable, because it's just not interesting, right? Okay. Okay, so we need an experimental design that can quantitatively filter the systematic effect of nuisances. Okay. Um, so another term for nuisance is controllable disturbance. Okay, controllable, it means that it can be anticipated and or manipulated somehow. Okay. All right. So in RCBD experiment, one nuisance factor is included as a block factor in the design. Okay. Now recall that blocking amounts to organizing the experimental runs into several groups, blocks, okay, each with a degree of homogeneity. Okay. Example: in an experiment done by a team of two students, okay, your penelitian 1, penelitian 2 work, okay, and the easiest way to include a block factor in your experiment is, as an example, all runs for replicate number 1, ya. Jadi percobaannya diduplo, replikasinya ada 2, okay. So replicate number 1 are done by student A, while all replicate number 2 runs are done by student B. Okay. So that effectively divides your runs into 2 blocks, block A and block B. Okay. Ensure that experimental runs at each factor level is replicated so that all block levels are included. We will see later on in the next page. Okay, and the order of execution of runs within each block must be randomized. So this is the word randomized in RCBD comes from. Okay, so again, the term random in RCBD refers to the way we execute runs within each block. It has to be randomized. Okay. But between blocks, randomization is not really necessary. Okay. Again, it will be clearer when we discuss specific examples. Okay. Result data of RCBD experiment will be analyzed using a two-way ANOVA. So, and the reason why we use two-way ANOVA is now we have two systematic factors. Okay, one is the experimental factor itself, and the second one is the block factor. Okay, which is systematically designed into the experiment. So it is as if we are doing a two-factor experiment, right? But again, one factor is the experimental factor, and the other one is the nuisance factor or the block factor. Okay, so now the systematic part in the Anova model, okay, becomes two. So now we have two systematic components, SS treatments and SS block. Okay, now let's see what the Anova structure looks like. Yeah. This is now the sorry, I want to make this consistent, so let's take, well, yeah, X is fine because the rest of the formula is written in X's. Okay, anyway, this is your individual measurement data. Okay, sorry about this. In the previous subsection I used Y, here I'm using X. Clearly I'm quoting different references. Okay, anyway, so hopefully you still get the point, right? So this is again X sub IJ, this is the individual measurement data. Jadi X sub IJ, ya X IJ ini adalah data-data individual hasil pengukuran kalian. Data percobaan ya, data mentah. Okay. So each of these measurement data can be represented as a sum of, again, global average plus treatment level effect plus block level effect, beta sub j. So beta sub j is block effect. Okay. And as usual, it ends with epsilon or error, random error. Okay. So if we sort of codify this model, we say SST equals SS treatment plus SS block plus SS error. Okay. And these are in the blue box are the formula for each of those sum of squares. Yeah. So now again, you see the difference, right? Because now we're adding one more factor, which is the nuisance factor or the block factor. So now the way we partition the total variance is different. Now we're adding one more systematic component. Ya. Jadi karena kita memasukkan komponen blok, ingat dalam konsep RCBD, blok ini kita masukkan sebagai suatu variabel kedua, ya, bukan variabel percobaan, tetapi variabel blok, ya. Jadi secara konsep, secara apa ya, secara substantif gitu ya, yang namanya variabel blok itu adalah sesuatu yang kita yakin bakalan mempengaruhi hasil percobaan, tetapi bukan dia variabel percobaannya, gitu loh. Jadi ya itu tadi, misalkan kalian melakukan percobaan dengan partner kalian, dan antara kalian dengan partner kalian itu hasil pengukurannya beda. Ya. Itu kalau mau, kalian bisa menyaring pengaruh perbedaan pelaksana praktikum dengan menggunakan percobaan RCBD, di mana identitas si pelaksana menjadi variabel gangguan, menjadi variabel blok. Ya. Oke. Okay, and then on the right-hand side, we can see the Anova table. Okay, as usual, we usually start with the sum of squares and then the degree of freedom of each sum of squares, and then sum of squares divided by degree of freedom results in mean squares. Okay. Okay, except this one, we don't have, we don't have the total is not, you don't need to calculate the mean squares of total. Okay, so the summation happens here in the SS, not in the MS, but in the SS. Ya, jadi penjumlahan aljabarnya itu terjadinya di SS sum of squares. Ya, ini bukan sekedar simbol, tetapi memang secara matematik demikian. Jadi SS total sama dengan SS treatment ditambah SS block ditambah SS error. Oke, kemudian masing-masing SS ini kita bagi dengan derajat kebebasan masing-masing, kita dapat MS. Oke, so all that is left to do is to perform the appropriate F test. Okay. And since we have two systematic components, then we can perform two separate F tests. Ya. Jadi kita bisa melakukan dua uji F yang nggak berhubungan satu sama lain. That's an important concept. Tidak berhubungan satu sama lain. Kita sudah memisahkan, kita sudah mempartisi mana kontribusinya treatment level, mana kontribusinya block level. Jadi F-testnya dilakukan secara terpisah. Okay? So the two F-tests will answer the question, is MS treatment larger than MS error? And number two, is MS block larger than MS error? Okay? Again, these two tests doesn't have anything to do with each other, so we can perform them separately. Yeah. Okay, any questions so far? If not, let's take a look at one example. And by the way, we have prepared an assignment for you guys, so it's a homework. For a homework to work, okay, you must work alone, or you cannot copy your friend's work. Okay? Yeah, this is for you. Ya, jadi kalau kalian ingin mendapatkan manfaat dari kuliah ini, kalau dikasih PR jangan nyontek teman, ya, because it's absolutely of no use at all for you. You learn nothing if you copy them. Okay. You can discuss, of course. We expect you to discuss this with each other, of course, but we do not expect you to just copy your friend's answer because it's of zero value for you. Okay. Think about yourself. Don't think about your friends. Okay. All right, let's take a look at this example. So this is what is called in material science or material engineering as hardness testing, hardness test or surface hardness testing of metals. Okay, you will learn about this a lot more next year in engineering materials course, bahan konstruksi. Okay, so what we do in hardness testing, okay, so we typically have these pieces of metal specimens. Ya. Jadi ini adalah istilah statistika Indonesianya benda uji. Okay. Test specimens. Okay. So these are the samples that we to which we perform the hardness test. Right? And the way we do a hardness test is really quite simple. We have what is called a standard indenter. Nah, kata-kata indentor ini saya agak susah nyari terjemahan Indonesianya ya. So essentially, they will leave marks, permanent marks on the surface of the metal. So these indenters are pressed against the surface at the prescribed force. Yeah? And then when we remove the force and we pull out the indenter, there will be indentation mark on the surface of the metal, of the specimen. Okay, which is then measured by a microscope. And with some mathematical calculation, we can determine the hardness of the specimen. Ya, jadi indentornya ini ditekan pada suatu gaya standar ya, standard force dengan waktu tertentu juga, kemudian diangkat. Nah, dia akan meninggalkan bekas goresan. Ya, bukan goresan sih, itu indentation, bekas apa ya? Bekas gigitan barangkali. Oke. Nah, bekas ini kemudian kita lihat dengan mikroskop, kita ukur ya, kita ukur dimensinya dan menggunakan dengan persamaan matematik tertentu bisa menjadi skala kekerasan permukaan dari logam tersebut. Okay, now let's take a look at the case that we have now. An experiment is conducted to evaluate the effect of indentor type on the hardness measurement results. Jadi percobaan ini membandingkan ya beberapa jenis standard indenters. Ada 4 jenis standard indenters. Jadi tujuannya adalah membandingkan hasil pengukuran antar indenter. Oke, mesti dicamkan dulu ya. Jadi tujuan percobaan ini adalah ya evaluate the effect of indenter type on the hardness measurement results. Ya, mengukur efek jenis indenter terhadap hasil pengukuran kekerasan permukaan logam. Okay. Now, the problem that we're facing is typed in bold here. It is suspected that the hardnesses of the metal specimens, sometimes if they take the form of thin sections of metal, we call them coupons. Okay, so we suspect that the hardness of the metal themselves are not homogeneous. So from one piece of specimen to the other, we suspect that there are variations in the hardness of the specimen itself. So if we're not being careful, if we don't filter out the effect of this sample hardness variation, they may interfere as nuisance factor. Oke. Jadi dicurigai logamnya sendiri kekerasannya bervariasi. Ya. Antara satu keping dengan keping yang lain ini kekerasannya nggak sama. Jadi kalau kita tidak memfilter, kita tidak menyaring pengaruh variasi tadi, maka seolah-olah variasi kekerasan antar sampel ini akan menjadi variable nuisance. Yeah. So therefore, we select an RCBD experiment to filter the effect of the coupon number, okay, coupon identity. Coupon or batch number. So we treat the coupon number or the specimen number as the block number. Yeah. So 4 coupons were used for the experiments. Okay. As appropriate for an RCBD experiment, each coupon was tested using all 4 indenters. Okay. Now, it doesn't have to be symmetrical like this. Okay, so if you have, in this example, we have 4 treatment levels, right? We have 4 indenter types. Now, we're not saying that the number of blocks have to match the number of treatment levels. It doesn't have to be. That just so happens what we observe in this example. Ya, oke. Jadi gini, saya ulangi dalam bahasa Indonesia. Dalam contoh kita ini, treatment levelnya ada 4, ya toh? Ada 4 jenis indenter. Ya. Nah, nggak harus jumlah bloknya itu juga sama-sama 4. Nggak sama juga nggak apa-apa. Tetapi memang secara statistik kalau jumlahnya sama, okay, so statistically it is actually favorable to have equal number of levels between the experimental factor and the block factor. We call those kind of experiment in which the number of levels are equal for all factors as balanced experiments, and they tend to give us better precision in when we process the data. Ya, jadi kalau jumlah level dari treatmentnya itu sama semua untuk semua faktor, itu namanya percobaan berimbang, balance experiment. Nggak harus kayak gitu, tetapi balance eksperimen ini cenderung menghasilkan, memberikan hasil ANOVA yang lebih bagus, memberikan presisi yang lebih bagus. Jadi selalu dianjurkan balance. Contohnya ini ya, jumlah level faktornya ada 4, jumlah blok levelnya pun juga di set 4. Nggak harus, tetapi sebaiknya begitu. Okay. Alright. And these are the results of the RCBD experiment. Okay. The hardness is given in mole scale. You can browse in the internet what is a mole scale. Yeah. These are the types of indenter. It is given simply as A, B, C, and D. And this is the block number or coupon number. Right? Okay. So this is data for coupon number 1, coupon number 2, and so on. Now, number one rule of RCBD is that each block has to receive all treatment levels Ya, aturan nomor 1 dalam RCBD, pastikan bahwa setiap blok itu menerima semua level treatment. Dalam hal ini, ya, setiap blok, setiap kupon itu harus menerima, harus diukur dengan keempat-empatnya indenter. A, B, C, dan D. Harus, nggak boleh ada yang, nggak boleh misalkan gini, misalkan yang blok nomor 1 ini hanya menerima indentor A dan B saja. Yang blok nomor 2 menerima indentor A, C, dan D, misalkan itu nggak boleh. Jadi setiap blok harus menerima semua level perlakuan. Okay, that's rule number 1. Rule number 2, the order by which the indenters were applied in the actual execution of the experiment has to be randomized. So you cannot perform, when you actually do this experiment in the lab, you cannot do it like this. Okay, so this is run number 1, that's run number 2, run number 3, run number 4. And then you switch, and then to change to a different coupon, and then you run the same order again. A, B, C, and then D. No, you cannot do that. But you have to randomize the order within each block. Okay. So for example, coupon number 1, the actual run order might be B, A, C, D. Okay. And then in coupon number 2, it's D, C, B, A. So whatever, you need to randomize the order of indenter type within each block, within each coupon. Okay. Okay, hopefully that's clear enough. Okay, so that's where the letter R, or randomize, comes from. So you have to randomize the run order within each block. Okay, and this is the box plot of the metal hardness, okay, of the measurement results. Okay, blue one is indenter number A, this is indenter number B, indenter number C, and indenter number D. Okay, right? Again, the question is, are there any significant difference in hardness values measured by these different indenters? Okay. Never ever jump to conclusions, guys. You have to go you have to go about this in a systematic manner, meaning you have to do an Anova analysis. Okay. We engineers have a really bad habit of jumping to conclusions. Okay, and actually, one of the mission in statistics is to prevent you from doing so. So we always have to question our data, our measurement results. Okay. All right. So this is the data. This is the raw data, right? And if we calculate average vertically within each block, then what we get are block averages or block means. Okay. And these block averages are then used to calculate the block sum of squares. Okay. Conversely, if we take the treatment, if we calculate the average horizontally, okay, across each, within each type of indenter, this type of indentor. Indentor. That doesn't look good. Anyway, I'm not gonna. Okay, anyway, just keep it that. You know what that means, right? Type of tip. This is indentor tip. Okay, so if we take the if we calculate the average horizontally, then what we get is called treatment averages. And then the treatment averages are used to calculate the treatment sum of squares. Okay, so this is a two-way ANOVA. Yeah. A two-way ANOVA that we and I will show you how to do this in Excel right about now. So now we get two systematic effects, okay, indenter type and block effects, yeah, and these are the p-values of each of those effects, yeah. Now we can interpret the p-value individually, okay, separately from one another. Okay, so for example, here, this would mean that both the indentar type and the block variable both are significant. Both significantly influences the value of the response or the hardness of the metals specimens. Okay, let me repeat that. So between these two factors, indentar type and block, both significantly influence the hardness of the response. We can see that, we can judge that based on their individual p-values. So each of them have a p-value that is way lower than alpha. Even if you use alpha of 1%, these values are still much lower than 1%. So those two variables, those two factors, both are very, very significant. Okay. Can you nitpick and say that this one, the block variable is more significant than indentar type because it has lower p-value? Yeah, you can. Okay, but that's not it's not a very useful or fruitful argument because both of them are significant anyway, very significant. Okay, now the question that I get asked most from the students is that, does this mean that this experiment is wrong? No, it's not wrong at all. It has done its job perfectly, in the sense that we are able to filter, to separate the effect of indentar type and the block variable. Okay, so you see here, right? The effect of indentar type is written on a different line. Jadi ditulis pada baris yang berbeda dengan efek blok. Artinya secara matematik kita sudah memisahkan pengaruh blok dengan pengaruh variabel percobaan utama. Ya. What you see, these are numbers. These are numbers that correspond to each contribution. So these are no longer mixed up between the two factors. Ya, jadi angka-angka ini masing-masing adalah milik dari efek tersebut. Yang baris ini angkanya adalah angka milik tipe indentor. Yang di bawahnya ini adalah angka-angka milik dari faktor blok. Mereka sudah terpisah satu sama lain. Oke. Ini bukan berarti percobaannya salah, nggak sama sekali ya. Jadi justru percobaannya sudah berhasil memisahkan pengaruh blok. Okay. So this p-value, for example, let me return to this number again. So this p-value really belongs to just indentar type. It has been separated. It has been purified from the influence of the block variable, of the nuisance. Okay. So you can safely draw any conclusion based only on this value. Okay. So here you can easily draw the conclusion that yes, the indentar type indeed influences the hardness. Okay, and that's it. You can also highlight the block if you want to. You can also discuss the block. You can say that, okay, in this experiment, it turns out that there are variations of hardness between the samples, which we have taken into account as a block effect. Okay. Ya, jadi ini p-value ini yang kalian lihat ini adalah betul-betul murni miliknya tipe indentor. Jadi kesimpulannya dalam hal ini adalah, oke, jenis indentor memang betul mempengaruhi hasil percobaan. Sudah, ya, pengaruh bloknya sudah kita pisah secara matematik. Okay. Now, any questions? If not, let's see how we do this in Excel. Yeah, I'm changing the tempo. I'm changing the way we teach a little bit in this week because I want to emphasize the Anova concepts to you guys. So that's why I'm not asking you to watch the videos. But of course, we expect you to see the videos afterwards. Yeah. Because it gives you a more detailed rundown of what we discussed today. Okay. All right. So let me stop sharing this one and let's see what we have in Excel. Okay, so let's yeah, this is weird. I'm not seeing anything here. Anyway, let's close that and repeat that. There we go. All right. Type door type. Okay, A, B. Yeah, that's fine. A, B, C, and D. And then this is the block number 1, 2, coupon number 3, 4. Okay. 9.4. And this one. Yep, okay, that's correct. So now we invoke the data analysis menu. Okay, so what we have here is this one, two-factor ANOVA without replication. Okay, so as you can see, we have no replication within the measurement data itself. Okay, so now can you guys see the data analysis pop-up menu? Can you guys see it?
No, sir.
All right, that's fine. It happens with Microsoft Teams, but anyway, so let me just show you again what I did. So I click data, okay, and then I click data analysis here, okay, and then from the drop-down menu, from the pop-up window, I select two-factor ANOVA without replication. Okay, so let me write it in the chat box. Okay, so we choose, so in Excel, use data, okay, data menu, and then sorry, no, wait, yep, data, and then data analysis, and then it will give you a pop-up window, and from there choose Anova two-factor without replication. There you go. You're not seeing anything now, right? You're not seeing any pop-up window again?
Yes, sir. I think you need to share your whole screen, sir. So like not the Excel
Right.
tab,
Okay.
like screen.
All right, got it. Screen. Okay. All right. Let me repeat the whole process again then. Okay, so here, click data and then click data analysis. Now, can you see this? Can you see the pop-up window?
Yes, sir. Now we can see the pop-up window. Thank you.
All right, good. And then from this data analysis toolbox, choose this one, Anova two-factor without replication, because that is what our data entails. So if you can follow my my cursor on the left-hand side, so this experiment essentially did not involve any replication. So each combination of indented type and coupon number is only done once. Okay, each combination is only done once. All right, so click OK there. Input range. Okay, one. Okay, so highlight everything there. Now you can also see the way I highlight my input range is I included the labels. Okay, I included the labels for variable number 1 and variable number 2, or this one is a row variable and that one is sorry, this one is line variable and that one is row variable. Okay, geez, I'm not making any sense. Sorry, this one is row variable and that's column variable. Okay, anyway, so activate labels and then you can choose whatever value of alpha that you have to work with. Then output range as usual, let's just set it up here and click OK. Yeah, there you go. Gee, sorry about that, there's a phone incoming phone. It's gone. Right. Okay. Who was that? Listed number. Anyway. Okay. So this is the indenter type. So this would be the row variable. And this is the block number or the column variable. Variable baris dan variable column. Okay, count meaning there are 4 data points for each indenter type. Okay, right, 1, 2, 3, 4, 1, 2, 3, 4, and so on. Okay, and this is the Anova table of our example problem. Okay, so well, instead of calling indenter type and block number, so Excel just puts the result like this: rows, so row variable and column variable. You can override it, you can overtype it, of course. So row, we can say indenter type, we can change it to indenter type. This one is coupon number or specimen number. Okay. Yeah, so that's the sum of squares, degree of freedom. MS is, of course, SS divided by DF. Yeah, and F is, this one is MS indented type divided by MS error. Okay, if you you can check it. All of the formulas are lost, so all here are just the numbers, but you can check it, you can confirm it. For example, I want to recalculate that one. Okay, so that's MS indented type divided by MS error. There you go. Gives you the exact same number. And this one is the MS of specimen number divided by MS error. There you go. Yeah. And then Excel calculates the p-value of each of the f-zeros, and it also gives you the critical f-value if you want to use the traditional approach in hypothesis test. So in which case, what we do is we compare this one to that one. Okay, and because the f0 value is much way larger than critical f value, we can say that the effect of indenter type is significant. Likewise, we can say that the effect of specimen identity number is also significant. Okay. All right, any questions here?
Excuse me, sir. I have a question.
Yep.
Later on, is there a way to calculate the error SS value manually, or later in the test we can just cite from this Excel table?
Most likely, we will not require you to calculate them manually because it's just too long. So ANOVA analysis will almost always be done with computer.
Oh, okay. Thank you, sir.
Yeah. Okay. Now let's do some interesting, some fun exercise. Okay. Let's say that we ignore the effect of variation between coupons. Okay. So let's say that we reorganize this experiment as a single factor, fully randomized experiment, not an RCBD, and see what happens. Okay. So now we treat the block number as merely as a run replicates. Ya. Jadi kita coba sekarang bagaimana kalau kita abaikan efek blok ini. Ya, kita abaikan efek variasi antar kupon. Ya, variasi kekerasan. Jadi kita anggap seakan-akan ini adalah percobaan satu faktor murni, nggak pakai RCBD. Jadi, so in other words, these block numbers are now treated as replications, as mere replications. Yeah, let's see what happened. Okay, so we go back to data. This is just for fun. Okay, not really appropriate, but let's do it for fun. Okay, Anova single factor. Click OK. Yeah, and this is the input range is like this. Yeah, group by rows. Ya, jadi apa namanya? Hasil percobaannya itu dipilah-pilah berdasarkan baris, okay, and labels in first column. Okay, let's set the output range. Oops, over here. Let's put it here. Boom. There we go. Okay. Now, again, what I just did is I treat this RCBD experiment as a single factor fully randomized in which the block number is regarded to be replicates. Jadi seolah-olah ini percobaan satu variabel teracak penuh dengan 4 replikasi. Okay, yeah. And this is the Anova table. Now you can see there's only one systematic component between groups. Okay, so this would be indentor type, and this one is error. That's it. So we purposely ignore the effect of block. So what is your conclusion now? Is the indentor type significant? Does it significantly influence the hardness? Gimana kesimpulannya sekarang? What can you conclude from this p-value? Come on, this is an easy one. All you have to do is to compare the p-value with a reasonable value of alpha. Let's say that the alpha is 5%. So the alpha is 0.05, and your p-value is 0.2195 something. So can we say that the indentor type significantly influences the hardness?
Is it a yes, sir?
Come on, think again. How do you interpret p-value? We have discussed p-value in hypothesis tests, right? And actually, I have mentioned this a few minutes ago. So all you have to do is to compare p-value with the value of alpha. So if p-value in this case is larger than alpha, then the experimental factor is significant or not significant?
Not significant, sir.
It is not significant, right? Just like what you do in any hypothesis test. If you interpret the hypothesis test result based on the p-value, then a p-value of, if the p-value is smaller than alpha, then we reject H0. We reject the null hypothesis. Okay. Ya, mudah-mudahan masih ingat semuanya ya. Jadi dalam uji hipotesis, kalau kita menggunakan p-value untuk menginterpretasi hasilnya, maka p-value ini dibandingkan dengan alpha. P-value yang lebih kecil daripada alpha itu bermakna kita menolak H0. Oke. Dalam hal rancang percobaan, seperti yang sudah dibahas sebelumnya ya, hipotesis nolnya itu bunyinya adalah ya variabel percobaan nggak berpengaruh. Ya. Oke. So go back to your notes or to your class notes and to your video segments. So the null hypothesis for ANOVA is that the experimental factors does not or do not influence the results. Okay, so if that null hypothesis is rejected, then the conclusion is it is significant, right? Yeah. So compare this p-value with the ones here. Yeah. On the left-hand side, in this proper analysis, what we have is after we resolve the effect from experimental factor and nuisance, it turns out the experimental factor is significant. But on the right-hand side, when I on purpose ignore the blocking effect, now the conclusion is the other way around, is that the conclusion here is that the experimental factor is not significant. And this is wrong. We all know that this is wrong, and this is the effect of interference from the block. Yeah. Okay. So this example is to demonstrate to you guys how big the influence of a block can be, or a nuisance variable. Ya. Jadi di sebelah kanan ini yang saya lakukan tadi ya, ini kan saya secara sengaja saya abaikan efek bloknya. Saya anggap ini percobaan satu faktor teracak penuh dengan 4 replikasi. Dan ternyata hasilnya kalau di sini, ternyata tipe indenter nggak berpengaruh. Dan kita tahu ini salah kan, harusnya dia berpengaruh. Ini adalah nilai p-value yang sebenarnya setelah kita pisahkan antara pengaruh indenter dengan pengaruh nomor spesimen, antara variabel percobaan yang sebenarnya dengan blok. Ini kalau kita pisahkan, ternyata ketemunya variabel percobaan yang memang betul berpengaruh. Tapi kalau kita campur aduk antara dua pengaruh ini, maka seolah-olah faktor percobaannya nggak berpengaruh. Ini contoh ya. Belum tentu hasilnya gini sih, ya. Seandainya saja, okay. So if hypothetically, if it turns out that the block number does not influence the result, then perhaps if we ignore them and we perform the ANOVA as if this is just a single factor experiment, then it might give you also a significant p-value, perhaps, maybe. Okay. All right. Any other questions?
Excuse me, sir. Can you send the Excel file so I can use as a reference? Thank you.
What's that again?
Can you send the Excel file later so I can use as a reference? Thank you.
Oh, I could, but it's not going to be very useful because it doesn't contain any formula. What I recommend you to do is if you want, you can take a screenshot of this, and then you can try to play around with it by yourself. Okay, because there's no formula. Excel does not keep any formulas. You can see these are all just numbers. Okay, so what you need to do is actually rewind the recording of our class today and see what I did, because if I send you it's not going to be useful at all anyway. Okay.
Yes, it's using data analysis.
Yeah. Data, click there, and then data analysis. So hopefully you were here within the last hour, okay? Because I have explained this a few minutes ago, okay? So if you're asking that kind of question, I can. That makes me suspicious. Were you really there in front of your computer when I was talking about this?
Yes. I'm just confirming.
Okay. Yeah, I'm using data and then data analysis. Okay, and then this one here, Anova two-factor. Now, what I did in the second one, though, I used this one. This is when I ignore the blocking effect. Okay. All right. All right, now, again, please check your Microsoft Teams. We have posted a homework, okay? So it's there for your exercise. Please, again, for your own benefit, try to do those problems yourself. And if you have any problem, you can ask in our WhatsApp group or in Microsoft Teams group, or you can ask about it next week, okay? All right, if there isn't any more question, then I conclude the class. Next week, we will discuss a very important class of experimental design, which is the factorial design. Okay, and this Anova concept will carry on. Throughout the rest of the semester, we will you always use this Anova method to analyze experimental data. Okay, because it's so useful, it's much faster, and it's more reliable than the methods that we have used so far. Now, I'm not saying that all of the procedures that you have learned, like one sample t-test, two sample t-test, and so on, I'm not saying that those are useless. Actually, if you work in an industry, chances are you need to use those simpler methods more than Anova. Okay, but if you're a researcher, if you continue your study to master or to a doctoral degree, then chances are Anova method will be more useful for you. You will need it more than the simpler, the two sample or one sample hypothesis test. But in the industry, especially when the industry doesn't care too much about research and development, then chances are you don't use Anova too much. Okay, but who knows? If you're involved with R&D, with innovations, then there's a very big chance that you will need this Anova approach again and again. Okay. I know I do it in my research. Okay. All right. Thank you very much, and we'll see you next week. And don't forget to turn in the homework.
Yes, sir. Thank you very much.
Yeah. Okay.
Thank you, sir.
Sir.
Thank you,
Thank you,
sir.
sir.
Thank you very much, sir.
Yeah.